Hello and welcome. We're continuing with the second part of the first law of thermodynamics brought to you by Science Visualized. We already saw in the first part that work done in a system equals to minus P external, that's external pressure, times the change in volume. So if the volume of the gas in the piston could be changed in sufficiently slow steps, so you change the volume very slowly, so you assume what we call infinite equilibriums, then the change is referred to as reversible. So we say that the change is reversible if it's done in such a slow way so that you have infinite equilibriums. On the other hand, the change could be referred to as irreversible if the system is not allowed to reach equilibrium, so it's not allowed to equilibrate. For reversible work, pressure external equals to pressure internal, so those two pressures are equal. So we can now determine the reversible work under these reversible conditions, which equals to, from this equation we saw that work equals minus P external times change in volume, but now we know that P external equals to P internal, so we'll just replace the P external with P internal, so equals to minus P internal times change in volume, but now we are looking at small amount of work, and therefore we have to integrate, so that integral sign means that we're counting the total work done, which is actually an accumulation of all the small infinite equilibriums. We know from the ideal gas equation that pressure times volume, PV, equals to number of moles times the universal gas constant by temperature. So PV equals to nRT. If we divide both sides by volume, you end up cancelling out the volume, and now you have pressure equals to nRT over V. So we can substitute for P internal with this value here. P equals to nRT over V. So instead of P internal, we use nRT over V. And that's from the ideal gas equation. And now work reversible equals to minus. That's the same minus we see here. And then integral. And then now for P internal, we say that P internal equals to nRT over V. So nRT over V, we are integrating with respect to volume. Now looking at this equation, nRT, that's number of moles, universal gas constant, and temperature, so it's done under constant temperature, then all of these are constants with respect to volume. And because nRT is independent of volume, we can take nRT out of the integral sign, and now that nRT comes out, it becomes minus nRT, and now we can integrate dV over V because we still have that V. Now recall from calculus that if we integrate 1 over x with respect to x, the answer for that gives you natural log, so natural log of x, ln x. Applying the same principle, the integral of 1 over v with respect to v will give you natural log of v as the answer. And we are looking at it from initial volume to final volume. So when we expand that, it will be natural log of v final, that's final, minus natural log of v initial. Now again from math, if we say log of A minus log of B is equals to log of A divided by B. So we can apply the same thing. Natural log and logs are similar. You handle them the same way. So natural log of VF minus natural log of VI, it will be equal to natural log of VF, that's final volume, divided by the natural log of the initial volume. So now work reversible equals to minus nRT natural log of V final divided by V initial. Now for constant temperature, we call that isothermal conditions. Remember, thermal has to do with temperature. So iso is uniform or same. So constant temperature, isothermal conditions, then work reversible equals to minus nRT natural log of Pi over PV. So we will look at initial pressure and final pressure. Now, if you compare this equation to what we just saw, you saw that here we had Vf over Vi, but now when you're dealing with pressure, it becomes Pi over Pf. And the reason for that is because pressure is inversely proportional to volume. So that means natural log of Vf, V final, over V initial will correspond to natural log of Pi over P final because they're inversely proportional. So you can either use pressure or you can use volume. Now, when the work is done in vacuum, the amount of work done equals to 0 because that's free expansion. That means you have expansion, there's no pressure, there's no force that's blocking that. There's no external pressure involved. So work done in vacuum or free expansion in vacuum, or just expansion in vacuum, we call it free expansion, the amount of work done equals to 0. Thank you very much for your time. We're going to continue with the next section where we'll be looking at heat. And that's, we use the symbol of Q, either that Q or uppercase Q for heat. Thank you very much. Please consider subscribing to support the channel. Bye.